Hello, and welcome. Here we are at MCTM. I would like to say hi. My name is Will Rose, and I have been teaching high school math for 19 years in Silver Spring, Maryland, mostly pre-calculus and calculus, some other advanced classes as well, but all in high school. What are you doing here? That was my question to what I thought was going to be a full room. Why are you at MCTM? You can answer. You don't have to answer. What are you doing? What are you doing at this talk? This is the most boringly titled talk, I believe, in the entire pamphlet, I think. Rediscovering formulas through examples. So what's that all about? I don't know. We're about to find out. I'd like to actually help people, if possible, and entertain and enlighten, and to make this talk kind of like useful to people. So, okay, the problem is that if something is really useful, it's probably something that's important, and it's probably something that you've already thought about. So it's really hard to say anything new about teaching something about a part of education that's really central, which is what I want to talk about today. But I might not say anything new, but maybe I'll just say it a little bit differently than other people have said it before. Okay, this is a burst, so that's half an hour only. So I've decided that also means I can be less professional than usual or something like that. And there's only 4 people in this room, so I think definitely I can do whatever I want. Target audience pre-calculus teachers, that's more my specialty, but I think this applies, I think if you go down several grades and up several grades, so to speak, I think it's also relevant. Okay, so here's the plan. We're gonna ask some deep questions. I'm not going to give definitive answers, but I'm going to give suggestions, and I'm going to leave you with some ideas about some things you can do a little bit differently. Yeah, so today's about formulas. So there's this formula for a parabola, right? Let's do it. Let's do it right now. Let's come up with the general equation for a parabola. Ready? All right, let's go. I got this document camera right here. And this is the kind of thing that happens all across America, in every textbook, in every pre-calculus classroom. And usually it starts kind of something like this. You get a definition of the parabola, or it may start something like this. You get a definition of the parabola, and then you start doing some math. So suppose we have a parabola. We know what that is. There's a focus at Q0. The direction is x equals negative Q. And now we're going to get the equation. Okay. So, we got a little directrix, we got a little focus over here at Q, 0, like I said, and then you have, parabola, whatever. Okay, and so what do? Pick an arbitrary point P with coordinates x, y on the parabola, and then we apply the definition, which says that this distance equals this distance. Okay, and then it's possible to use coordinate geometry to make some sort of observations here. Okay, this distance was Q, so since this is x, that makes this distance x plus Q. And then this is y, and we have a right triangle. Since this is x, then that makes this x minus Q. And now we have some facts that we can take away from this diagram. That this type, if we call this, is the focus over here. And so I know that this distance FQ is the square root of x minus q squared plus y squared, that this equals x plus q. Okay, so this is totally standard. If you square both sides, then it all just works out. And this is hard or not hard, depending on who you are. So let me just focus for a minute so I don't make any mistakes with my Sharpie. Many things cancel, and we end up with y squared equals 4qx. Put a box around it, and this is now our formula. Okay, so, all right, I went a little fast. I would go slower if this is a pre-calculus discussion, but I assume everyone in the room kind of knows this stuff already. Then other discussions can be had about what happens if it's pointing the other way, if it's pointing up, if it's pointing down. Eventually we learn all these formulas. There's 2 of them or 4 of them, depending on how you think about it. Then there's some conversation about the fact that you have to modify the equation when the vertex is not at the origin. All right, so, everyone good? All right. Question. What have we accomplished exactly? What was sort of the point of that? Okay, so, well, here are some pros and cons. The pro is we have the general formula now. The general formula is very powerful because the general formula is general, and it will then be useful for all the kinds of parabolas that we're ever going to see again. The cons are that maybe students are lost. It really depends on your students, and it depends on the difficulty level of the derivation. This one's not so hard, but of course, what we're doing is already pretty high up the ladder of abstraction, because we have this general equation, which is meant to represent an infinite number of points, and in addition to that generality of that equation, we have sort of like an extra level of generality, which is that we're doing it for an arbitrary Q value, that's what I call it, the distance between the focus and the vertex. So maybe students just don't get it. So this is a potential problem. So all right, I am definitely not the first person out there to say, don't do it this way. Instead of doing what I just did a minute ago, you should probably, almost every teacher should probably do something else first. And the something else first is to do a specific example. This is already pretty hard and involves quite a lot of, challenging mathematics. Let's go. Same problem over again. This should be easier, way easier for students. For us, it might only be a tiny bit easier. Now we have our focus at -2, 4. So actually, it's not a completely analogous problem now because the algebra is going to be a little bit more difficult, perhaps. But let's go. So think about how I want to do this. Yeah. Something like this. So boom, 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 boom. Here is my directrix. My focus is at -4. And yeah, that means that my vertex will be halfway between. So my vertex is going to be here at 1, 4. And I'm going to get some kind of parabola that looks whatever it looks like, something like that. Okay, and then we go through a lot of the very same logic that we just went through. But now with numbers, so it's like easier. So now I pick some arbitrary point, x comma y, and what do I know? The distance to the focus equals the distance to the directrix, but now I can do it with specific numbers, because this is the equation x equals 4, and so this can be seen, this distance right here is 4 minus x, and that being -2, 4, there is a little triangle here. Let me kind of try to draw it. Boom, boom. And what can I say about this triangle? Well, this leg is x plus 2, because, and this distance here is, well, point P has height y, so this is going to be y minus 4. Yeah. And now we just do the logic all over again, which is we say that these two things are equal. And so what do I know? I know that this distance FP is going to be the square root of x plus 2 squared plus y minus 4 squared, and this is the same as 4 minus x. Okay, and now we have some algebra that's, well, it's just less abstract. You just no longer have this q in the way. And I feel like this, most students can probably just do without any problem. It just feels more real, just with the extra level of numbers. Okay, let me just sort of do this kind of quickly. Or maybe I've even proven my point and we can stop. I don't know. But when you expand this all out, plus 4x plus 4, here I know from experience that we should just leave that one alone. But some cancellations happen, and we end up with y minus 4 squared equals something. Let's see, 12 minus 12x. Yeah, that sounds about right. And if I, yep, that's exactly what I'm going to do. Factor out a negative 12, then you get x minus 1. Okay, so I'll give this also a smiley face because this was doable. All right, was this easier? Was this harder? I think it's easier for students. It's still pretty hard though, and it's still sort of genuine mathematics in a way, and it's just less abstract. Okay, so back to the presentation. This was kind of an extended example. You have to meet students at the correct level on the ladder of abstraction. Jumping right into the general formula can, I think, be disorienting for some students. It depends on the students, depends on their mathematical maturity, it depends on the difficulty of the topic. It's probably true, even for, I personally teach students who are quite mathematically inclined and talented, and they're also very enthusiastic about math, and they've been through quite a lot of math already by the time they're in my classroom. Still, they struggle in a way that surprises me with tasks that are more abstract than they possibly need to be at that moment. And I have started doing a lot more of this, do a problem first before doing the general formula. So solve a particular problem, then move to the general case. Okay, and I guess to evaluate, whether this is sort of better or worse or something like that, we have to ask all these kinds of, I will now ask a whole bunch of obnoxious, kind of very general questions. Like, what are we doing? I'm not going to answer any of these questions. What are the goals of this mathematical classroom? What are the goals of this activity? Why do we actually care about parabolas? Why should the students care about parabolas? What comes next for the students? They kind of want to know, like, where's this going? And where it's going is going to affect, judging how successful what we've just done. And are we doing math? I guess we're doing math. Who is doing math? If the teacher is doing too much of it, then that's its own problem. And okay, what's the takeaway the students might ask? What am I supposed to know about this formula? There's often a question where students look at you and they say, am I supposed to be able to have done that myself? Is a kind of a question they don't always articulate, but it's kind of present in the back of the classroom. So what do we expect from students after you get this parabola formula? Do we expect them to just now subsequently use it, or do we expect them to be able, in the future, on the spot perhaps, to derive the equations of other geometric objects in a similar way? Okay, so this, I think the answer in most mathematics classrooms is you are expected to just use the formula. I think what is happening 99% of the time, including my own classroom, by the way, I'm not so much better, is the following. You then get, after this formula derivation, you then get this same problem. I'm just going to do this same problem over again. It's going to take 1 minute this time, because that's the great thing about having a formula. Here is my directrix. Here I go to my focus at -2, 4, and then know where my vertex is. It's over here.
Oh, document there.
Oh boy, thank you. And then I have, like I said, 1, 4, my vertex, and then I recognize that this distance is 3. Therefore, Q equals 3. And now I sort of pull up from my mind somehow a supposedly memorized fact that, I guess, that, parabolas that are looking like this are x equals y squared parabolas, and therefore this is going to be a y squared equals 4qx type situation, but actually it's going to be negative because I have also somehow come to learn that when it's pointing left it's negative. And then I just take all this information and I kind of like stick it in. Given the fact that the vertex is at 1, 4, then I say that this is y minus 4 squared equals negative, q is 3, so that's negative 12x minus 1. And kind of like put a box around it. Okay, well, that's a very different intellectual activity that I just did right there. I think this is what students spend essentially all of their class time doing. It's what they spend their time doing on the homework, and it's what they spend their time doing on the tests. Kind of just plugging numbers into memorized formulas. All right, so now a little bit more maybe discussion or something like that. What is high school math? At some point, high school math can turn into a quest for formulas. It just seems like there are a lot of formulas out there, and our job as math teachers is to just start plowing our way through all these formulas, and the kid's job is to learn it. And what happens is that there's this struggle. There's these 3 phases. This is me imagining the mind of a student. First, you struggle to acquire the formulas. It's quite painful because it involves a lot of thinking. That's kind of hard. Then you get the formulas, and when you get the formula, we have the formula now. And once you have the formula, now I guess you memorize them. I guess you write them down. I guess you study them, learn them, whatever that means. And now everything is easy. Life is good. We got the formulas, now we relax and we don't think anymore. And additionally, there is a kind of a weird dynamic that emerges between the teacher and the student where we seem to be the guardians of the formulas. We have the formulas and they want them. Cryptic movie reference. Not cryptic, but just obscure movie reference. But you know, the students are very much, or some of them at least, at the beginning of class, they just want to know the formulas, and they're kind of just waiting us out. Give me the formulas. Give me the formulas. And the teacher, these are the teachers with integrity, are like, no, you can't have the formulas yet. First, we need to prove them. You need to prove yourself that you deserve these formulas. And after they get the formulas, now it's somehow you've earned it, and now you're allowed to have the formulas, and you somehow now are supposed to memorize them, I guess, or understand them, or maybe there's going to be a formula sheet, maybe not. Also, we need to talk about potentially, forgetting the formulas, because they're easy to forget, and you're not supposed to forget them. Okay, so here's my quick, how to teach. You can solve a specific problem, which I was indicating was a good idea. Oops, sorry. You can derive the general abstract formula, the general case, and then there's this kind of mindless formula regurgitation that's going on, where you use the formulas. Maybe that's a little bit too harsh. Okay, and so what's probably best? What's probably best, if you have the time for it, is to, like I was saying earlier, solve a specific problem first, which in some ways gets the students engaged, it's easier, it's less abstract. This motivates students and prepares them to be able to do the general derivation, which is usually a bit harder. This is obviously more time consuming, this is why a lot of people don't do this. And then mindless formula regurgitation. This is like the best you can hope for, maybe. And then option 2, which is what a lot of teachers do and a lot of textbooks do, because it is faster, I think, is to skip the solving a specific problem. Say you go straight for the derivation of the general formula. This is probably bad because students are lost and they're feeling like they could never have come up with this themselves. It's just too hard. And they're just going to wait it out, frankly, until you're done with your proof, and then realize that that part is really not important because they're not going to be assessed on it. Option 3, which I think is defensible on a case-by-case basis, is to not derive the general formula at all. To spend your limited amount of math time solving the specific problem, and then simply skip the general proof and just say the general formula is exactly analogous to what we just done. And then I'm not even going to talk about this, but indefensible, but is probably happening in the majority of math classrooms in America, I would say, is that you're just not doing any derivations, and you're not solving a specific problem, and you're putting the formula on the top of the handout, and then you're just spending your time on formulas for the whole unit. Okay, so finally, with 5 minutes left, I'm here to now explain what the real point of this talk. The real point of this talk is there is one more twist to the story, and the one more twist to the story is after you do all of these good things I said you're supposed to do, occasionally you can just not use the formulas. So there's this option 4, which is just, I refuse to use the formulas. And this is sometimes practical and sometimes not totally practical. But a mixture, after you do the motivating example that gets you to understand the logic of what's going on, after deriving the general formula, when it comes time to just, when you're in the phase where you're just doing mindless formula regurgitation, every now and then, as time allows, just don't use the formula. Okay, so what I mean by this, so what I mean by this is when given this problem, in class, let's suppose that you did great things. Let's suppose that you truly did the full-on derivation, and perhaps even your students understood it. Just because they understand it one day doesn't mean they understand it the next day, or a week later, or 3 weeks later. People do forget things, and if you don't use something, you just forget it. And this just feels like a one-off. So if you do something once, you're not going to really learn it. So, but let's just, assuming even you're doing your job like you're supposed to, you did all that, then this is just not cutting it. Just doing this is just not good enough. Every now and then, after a week later, 2 days later, 3 days later, just do one of these. In other words, well, say going over the homework on parabolas, and they had to do 8 of these parabola problems, hey, 1 out of those 8, just do it all over again from scratch, showing them that this wasn't just a phase where we just, the part where you use actual mathematical thinking to reason your way through to the answer is not just something you do in the lead up to getting the formula, it's something that's available to you at any time whatsoever. All right, how are we doing? All right, I thought I would have a lot more time, but what I really have is like 5 more minutes. I don't think this is even, maybe I'll just talk these through without actually doing them. Ready? Here are 6 other examples I have thought of where it is reasonable, in my opinion, to be less efficient. And even after acquiring the formula, just don't use it. Okay, so let's go. When it comes to deriving the equation of ellipse, for example, this is, in my opinion, significantly harder. And this would be an example where I think every teacher, I'm talking about every pre-calculus teacher in America, should start with a case with numbers first. Basically, no student is ready for the full general abstract proof. And this is already quite hard. We start with the foci, we have this whole setup, and then, okay, you drop a perpendicular down. I think you all know the proof, so maybe this is not something I want to kind of spend time on, but again, you know, there's lots of sort of rich mathematics going on here. You have this green triangle that you can apply the Pythagorean theorem to, and this is x plus 4. You have this red triangle that you can apply the Pythagorean theorem to, and this is 4 minus x. And then there is the definition of the ellipse, and so what you end up with is the square root of x plus 4 squared plus y squared plus the square root of 4 minus x squared plus y squared equals 10. And then you're going to do this whole thing. This is quite hard, I think, and very challenging. The algebra is very challenging. However, students can do this. And if you've never done this before, it's the kind of thing where certain choices will need to be made, you know, later on in the derivation, but those choices are all very natural. And the presence of this healthy amount of numbers makes this a doable thing for students. Okay, and good? Okay. Then the general equation of an ellipse, by contrast, is just basically too hard for almost everybody. If you were successful in the thing I just had up on the board, then you might, if you really had a lot of class time, you might also want to do this. And I think students could be successful with this, having done the previous problem. But there's quite a bit of extra thinking and extra skill that's required to make progress with the general case. So this would be an example of a problem where I feel like it's very defensible to do the particular equation and then not do the general case at all. Okay, but that's not really in keeping with what I wanted to talk about today, because what I wanted to talk about today was more of this extra new thing. This extra new thing being, after you derive the general formula, not using it. And this is an example in which I think that's very possible. For example, here, this is a famous thing that everyone is doing in pre-calculus, finding the terms of an arithmetic sequence. How do you do it? There's this kind of Gauss method where you write the sum backwards and you get, this, and then count going down by d each time you end up with a plus d over here. And so you've written the entire sequence in reverse. Is quite hard. Notice the very high level of abstraction because there are so many variables here that it's very hard for students to maybe keep track with what's going on. But when you all add these up, you get 2a plus n minus 1, or sorry, what's happened here? 2a plus, oops, this should be, let's pretend that didn't happen. This starts with a, so that's why that is looking like that. And we'll do this. Everyone forgive me? Okay, good. So what you end up with here is a whole bunch of columns that all add to 2a plus n minus 1d. And how many of these columns do you have? You have n of them. Getting a little sloppy here. And so this is why the formula for the sum of the first n terms of an arithmetic sequence is n over 2 times 2a plus n minus 1d. So abstract that I confused myself for a second there. Okay, this is fine, and probably you need to do this, and everyone does this, and you should do it. However, suppose it's 2 weeks later, and students are like, what the heck is that formula? Students find this formula very difficult to memorize for whatever reason, and they just don't like it. Take, by contrast, this problem, which can be solved with the formula. I would call that the standard way, so in the interest of time I won't even show it. Instead, you can just do this problem, because I think I do need to stop, and you can just be like, okay, I need to add a bunch of terms there in an arithmetic sequence. Well, if I start with 3, and I am going up by 5, then I have to add 5 n minus 1 times, and I eventually end up at 58. So that means that n is 12, so I have 12 of these terms. And instead, it's quite refreshing, and I feel that almost nobody does this, to just write the terms backwards. So down by 5, etc., and just go all the way until you get to 3. And look at just how easy this is. Probably easier than using the formula, frankly. Is to just refuse to use the formula. And you then have, 10 of these, and 12 of these rather. And so the sum is going to be 12 times 61 over 2, and that's 6 times 61, so that's 366. Okay, this is superior to using the formula because you are actually doing some mathematics, and you are, by solving the problem this way, perhaps it's a tiny bit less efficient, but you are refreshing their minds about the actual logic and the math that went into proving the formula in the first place. Okay, I'll just throw some more slides up. It is also very possible, but I'm out of time, to prove the law of cosines, to solve the law of cosines with a particular example. This would be a great thing to do before trying to prove the law of cosines, and it flows very, very naturally from this picture. You drop a perpendicular. If you've never done this before, it's very easy. The product rule is another example of a thing that people prove once, and then perhaps even in a best case scenario where they're drawing this rectangle and they're speaking geometrically, in order to get the formula, subsequently it's just using the formula. Whereas you could just draw the picture every single time. Again, I'm out of time, but maybe I'll add to this video a little bit after I let people leave, explaining how you can sort of go through the logic of the product rule very quickly to sort of explain in a redundant kind of way. And another one, maybe less interesting, but if you want to come up with the formula for the inverse of a 2 by 2, even after your class has best case scenario derived the formula, you can just do it again, from scratch. That's probably a good use of class time. And it is quite easy and straightforward. Okay, so basically, be redundant, be less efficient, go back even after deriving the general formula, and just every now and then redo it over again using numbers to remind everyone what's really going on. That's really the theme of this talk. Okay, I'm well over time, so I'll stop there. If anyone has any burning questions, you can just ask me after, because there's only 4 people in this room. So here is who I am. You can email me if you want these slides or something like that. Otherwise, thanks for coming to the talk, and I will probably pause this or something. Any questions? Am I that over? I feel like that clock's a little fast. 12, 3 minutes over. Sorry about that.
It's okay, that's good. Do I have any questions?
I'm gonna show you stuff. All right, goodbye. All right, we're back for a bonus round. We ran out of time, but what's time anyway? Let's show this. I would consider to be the problem that you should give students before attempting to prove the law of cosines in general. So this is a case where the law of cosines is applicable. This is an SAS triangle essentially, and honestly, it's pretty easy. You drop a perpendicular, then I don't think it matters so much which one you do, but I will call this x, and this is therefore 6 minus x. And now we have 2 triangles. This one in blue, and this one in green. And then we can give this altitude a name. We can call it h, which is kind of standard. And now what can be said about this situation? Well, looking at the blue triangle, clearly c squared is just 6 minus x squared plus h squared. And then you can replace h squared using the green triangle with what it is, which is just 7 squared minus x squared. And here I'll keep it sort of general or something like that by continuing to write it as 7 squared. What do we end up with here? Well, we end up with 6 squared minus 2 times 6 times x plus x squared plus 7 squared minus x squared. The x squareds cancel, and you get 6 squared plus 7 squared minus 2 times 6 times x. And of course, what is x? Well, x is just 7 cosine 35. And so this is 6 squared plus 7 squared minus 2 times 6 times x is 7 cosine 35. Okay, in order to prove a point, sort of didn't simplify as I was going. A student probably wouldn't do that. The student would probably just simplify as they were going, but then they would get in a pretty straightforward manner, especially if you were guiding the process a little bit, the answer to c squared. And then they would sort of understand that it is a matter of pure sort of calculation, given one of these SAS triangles, to solve for the side opposite the given angle. And ultimately, it boils down to dropping a perpendicular, making this kind of variable choice, applying the Pythagorean theorem twice, and then recognizing that the base of one of the triangles can be labeled with 7 cosine 35. Okay, so this is not that hard, and I think if you do this, you can take this directly into a proof of the general formula, which I think probably every classroom should do. And it's exactly analogous, and the law of cosines proof just falls into your lap. This is something that, again, everyone's learning it, but I think a lot of teachers feel that this proof is somehow hard. In this case, I don't. think it's so hard if you do a preparatory example like this. Okay, more in keeping with the theme of the lecture, though, the product rule. This is something I feel like nobody is doing. I think a lot of people do nowadays, especially, give this kind of diagram in general, in which you think of the product of two functions as the area of the rectangle, which has those functions at side lengths. And then there is this sort of argument where, f gets a little bit bigger, g gets a little bit bigger. And so, okay, this is not so revolutionary to prove the product rule this way. And since this is fg, then the overall change in the function is just f times delta g and g times delta f. I recommend doing this, and I think that people do this, and that's good. But what no one does, as far as I know, basically, is continue to draw this picture, the following day, or even the following minute. So just after this big lesson on the product rule, where you explain the point and the idea of it, and how to think about it, and how to understand it, and you set up all this geometry, and you do this whole proof, which is quite involved, then it comes time to doing the examples. And once again, in my opinion, there's this sharp sort of cliff where we're doing this highly intellectual, highly abstract activity. We have the formula, and then we just promptly seem to instruct the students, if not explicitly based on our actions, to forget all of the logic that went into the formula, and now just simply mindly use it. Where there's nothing wrong with, and in fact it is enlightening and simple, in this case not even time consuming, to continue to draw this rectangle out, at least for the first day or two, while you're using the product rule. And here you can, sort of observe that that the derivative of sine is cosine, and so the change in the sine function with respect to a change in x is cosine, and therefore the tiny change that you would expect in the sine function is basically just cosine x times delta x. Similarly, let's see, where do I want to write this? Somewhere else. The change in the x squared function with respect to a change in x is 2x. And so the change in the x squared function is just 2x times delta x. And so if you let the sine function get a tiny bit bigger, well, you end up with this being the tiny change that you would expect in the sine function, and this being the tiny change that you would expect in the x squared function. And so you have the function x squared, and so you can sort of just do it with this particular example. We can see that, that here we get x squared times cosine x delta x, and here we get sine x times 2x delta x. And here we get the product of those two, which kind of goes to 0. And so, all right, with respect to x, the derivative of this particular function is, sine x times 2x plus x squared times cosine x. But here, somehow seeing it with particular functions drawn on the rectangle, I feel like it's powerful for students, and it shows, again, it's a connection between the derivation of the formula phase and the solving problems phase, that they're not just two completely disconnected things with just a formula linking them. In fact, you can continue to sort of think as you solve the problems. Okay, one more. This is maybe like less impressive or something, I don't know, maybe, or just more boring. But if you want to have students find the inverse of a 2x2 matrix, there's a formula. I don't know what most teachers are doing. Deriving this formula is actually, pretty annoying. Not impossible, but pretty annoying. But you don't have to either as a prep for it, or after, if a student forgets it or something like that, you can just always do it all over again and ask yourself, well, what even is the matrix? That is the inverse of this given matrix here. Well, it's the matrix that you get when you multiply by this matrix, gives you back the identity matrix. And so now, if I can just solve for those 4 variables, like, I'm just done. And here you can just apply the definition of matrix multiplication and just see, well, I'm multiplying row 1 and column 1, 2x plus 3z is 1, but multiplying row 2 by column 1 gives me x plus 5z is 0. And now we just have a system of equations which can just be solved. And here, doing it again, if you multiply row 1 by column 2, you get 2y plus 3w equals 0, and row 2 by column 2, you get y plus 5w equals 1. And now you again have a system of equations. And here, let's see, I already did this, but I'll just do it again really fast. You multiply by 2, and then I guess I will subtract. Then z is negative 1/7, and if z is negative 1/7, I can see that x is going to be 5/7. So that's pretty easy. Over here I'll do something similar. 2y plus 3w equals 0. 2y plus 10w equals 2. Again, if I subtract, I get negative 7w equals negative 2. So w is 2/7, and if w is 2/7, then going up here, I get that y is negative, something different on my paper. So what's y?
Negative 3/7.
Y is negative 3/7. Yeah, okay. Yep. All right, so I don't know, this took like, what, 5 minutes? Okay, I was going a little bit faster, so it probably took me like less, but this is not so hard for a student. And so what is the answer to the inverse of this matrix? It is just the matrix consisting of 5/7, z is negative 1/7, and y is negative 3/7, and w is 2/7. Okay, what's the moral of the story? I'm going to stop doing math now. If you are going to be one of those, 1 out of 200 teachers, that's my impression, who does derive the formula by hand in sort of brute force style in general of the formula for the inverse of a 2 by 2 matrix, then you should certainly do this first, because this is not so hard and only really takes like 5 minutes. And do this first, then jump into the general case, and the students sort of already know what to do. And then also, you should, at some point mention, one time even is enough probably, while going over homework, 2 weeks later, and you look out in the room and you see that, a third of your class can't remember the formula for the inverse of a 2 by 2. Hey, if you're stuck, you can just do this again if you really, really need to. And you could even, do this on a test. It wouldn't be, so time consuming. If you can't remember how to derive the formula of a 2 by 2, you just do it. And especially if they've had this memory of doing this in class before, then this is reasonable for them. So, okay, there it is. I'm done talking now. I'll say goodbye to the internet. All right.